Okay, so what we're going to be doing here is walking through some material in SPSS where we're going to do various kinds of processes that are necessary for obtaining statistical tests, performing statistical tests, including the one sample t-test, the two sample t-test, and we may get to the dependent sample t-test in this session. If not, I'll make another video. So this is a different data set. It's called TC Reasoning or TC Reas with, you can see that it's SPSS is open in the high upper left-hand corner. You see the name of the data set. It's an old data set on reasoning of teacher candidates that I use sometimes for demonstration purposes. And the first thing you always want to do is you always want to look at variable view and try to understand what's in your data set. In this case, the people in the sample, it was a survey study, and the people in the sample took a assessment in one form or another, Form A or Form B. And I found that by looking at this form variable and seeing how it was value labeled. That is a Form A and a Form B. Plus, I know the data set or know how I've rearranged it for instructional purposes. The purpose of the study, it's actually a measurement study. And so, because I specialize in measurement, and so what I was actually trying to find out was whether there were differences in people's responses, depending on whether they completed Form A or Form B. So one of the things I'm going to look at right away, before I even go on to the other variables, is how many people I have and how many people answered each form. So to do that, I go under Analyze. You will already have done this. And I'm just going to get the frequencies of responding to, of categorization in this form item. So I'll know how many people took either form. And so when I ask for that frequencies, I find that in these data set, there are a total of 74 people who have a value for that form question at all. And of those, 38 took Form A and 36 took Form B. So my overall sample size is 74, and my N for the group that took A is 38, and my N for the group that took B is 36. So you see, already you might be thinking, I have two subsamples in this, an A group and a B group, and they're not quite of equal sample sizes. So if I wanted to compare them, it wouldn't be any fun to hand calculate it, and I'd have to be aware that the sample sizes were unequal. We're going to look at this data set some more. There's a variable about whether or not they consented to participate, their race, ethnicity, which is, I believe, the same thing as we've had before based on the old census categories. Male or female, the year of their birth and their age, so that sometimes you get a higher quality of response if you ask year of birth rather than age. Their highest degree, which you've seen in other data sets. If they completed undergraduate, their undergraduate major. Now that is called a string variable, which means if you look in the data view, that these are open-ended answers. And that's kind of a pain to analyze, and that would come into more advanced work in SPSS and is not covered in this course. But if you like did an independent study or something, I don't even think it comes in. It's really SPSS, not statistics. But string variables, just for your information, are text. And then whether they're a teacher or not, with various more categories than you would sometimes see. It's not just yes, no, but it includes student teaching and practicum. And then these various survey items. So this was a test of reasoning. And it started out with like all these syllogism items, which are things like, if A, then B, A is B true. And there are only 4 listed here, but I think on the actual test, there were a lot of them. Those are tests of logic. Then there are these things called AOTs, which are called an actively open-minded thinking scale. And the SRL scale is probably self-regulation. And then you have more of these other kinds of survey items that have been rescaled. This is a demonstration data set. So knowing the content of the project isn't very important, plus the content has been modified for instructional purposes. But the main point here is that I was trying to look at whether reasoning in terms of open-mindedness and logic was affected for students in a group that had a particular form of a test with slightly more motivational prompts than a test that didn't. And so whether the motivational components of some of the prompts resulted in higher performance on the syllogisms, or whether it or open-mindedness. Okay, so my dependent variables were syllogisms for logic and open-mindedness for open-mindedness. And I was looking to see if there were differences between form A, which had the motivational component, and form B. That's the main concept. Okay, so I know what my sample size per group is. You should always report your, for your basic descriptive statistics, you should look at the demographics of people. So we can go ahead and get the frequencies for all of those background variables, race, gender, degree, and teaching status. You don't want to ask for frequencies of a scale variable like a year or their age, because those are continuous variables and you'll just get lots and lots of things, one for each level. And so we see that 74 people answered all of these. So there are no missing data on those questions. Most of them were white. There's not going to be any difference between your percent and your valid percent because everyone had a value. And the 66% were white. They were half male and half female. So the sample was probably purposefully collected for gender. And they had either a bachelor's or a master's degree, with a slightly greater number who had a bachelor's degree. And most of them were not teaching, but more than a third of them were. So for instance, we could compare teachers versus non-teachers, but we're going to compare these two forms of the test. Okay, so another thing to do would be to do things like look at the age. Now, this came up in the first mini project, is one of the ways to analyze age would be found under analyze descriptive statistics. And you could do this under frequencies. So I'm going to reset that whole column. I'm going to ask for age over here. And I'm going to ask under the statistics for the mean, the median, the standard deviation, and I might as well ask for the minimum and the maximum. I'm going to suppress the frequency tables, because when I ask for age, I'm going to get like a lot of, 25, 26, 27, 28. I don't really want to know how many people are exactly 28. So I don't need the frequency of 28 occurring. I'm more interested in the central tendency. So I'm going to suppress that. I'm going to uncheck it. It's a default option. And so what I see is no one is missing on age. The mean is 25. The median is 23. So the mean is higher than the median, which means it's likely a skewed distribution. The standard deviation is 7.4. The minimum age is 18 and the maximum is 53. So this is actually a little similar to what was in the mini project, is that there seems to be a skew with a person or people at the high range of age. I know this was gathered among teacher candidates, so I'm surprised at an age of 53 for someone learning to be a teacher. Not at all unheard of though. So I'm going to go back to descriptive statistics, frequencies, where there is an option for charts. And I'm going to ask for the histogram. I could go someplace else and ask for a box and whiskers plot, which will pretty much show me the same thing. But in this case, I'm going to choose a histogram, and that I am obtaining under frequencies charts, both under descriptive statistics. So there's my histogram, and I see, just as I suspected from that value of 53, that there are a couple of advanced ages that are skewing the distribution, making it less symmetrical. So this is just something to report, and it's also something to say the distribution was positively skewed. Okay, the type of skewness is determined by the direction of the outliers, and therefore the median should be reported in addition to the mean, because the median is the appropriate statistic with a skewed distribution. And then you could report, mean 25.8 or 26, median 23.5 with a standard deviation of 7.4 or 7.45. So that's a part of describing the sample. But we have described the sample in the past, so I think we should go on to new things. So one of the things that we might look at is, for instance, something that you would come up with. By the way, a z-test is not available in SPSS. It's really not necessary. If you know the population, the standard deviation, the z-test can be done by hand in a matter of moments. So and because all you need also is the sample mean. You don't even need the sample standard deviation. So the z-tests are just not given they might be buried somewhere, but they're not under the normal options in SPSS. But you can do a one sample t-test. And something we might want to know is whether in age, particularly since we've seen that the distribution of age includes some pretty high values, we would consider that the age of these teacher candidates at Hunter College is different than the average age for the population of teachers. Or let's say of teachers graduating from a school of education. So I'm going to, for the purposes of demonstration, I'm going to provide an age. This is our target, our expected value under Bonner's assumptions. It's the value that we expect a typical graduate of a school of education to be, and that we want to use as a basis of comparison for our Hunter College group. So to do that, so we have one sample, which is these 74 people. We have an expected value, which I'm going to say is 25. That's the average age that we expect. Maybe it's from census data, maybe it's from union data, but for now it's from Bonner, that we expect that will be the average age of graduating teachers, teacher candidates, and that's 25. We don't know the standard deviation about that expectation. We don't even know if it's a mean. It's an expected value. Typically they're means, but in this case, it's just our expected value that we're testing it against. But we have a sample, so we can get a sample mean and a sample standard deviation. That case where you have a sample mean, all the raw data, you can get a sample standard deviation, and you have a value to compare your data to is the one sample t-test. And that is found under Analyze. And it's found under Compare Means. So if you look under Compare Means on the Analyze menu, you'll see a bunch of sub-menus, pretty much all of which you're going to do this semester. You're not going to use all the menus, but you're going to do all these tests. And you've already done the z-test, which isn't even on here. So the z-test you've done, the one sample t-test you've hand calculated, the independent samples t-test you've hand calculated. This isn't really anything. It's redundant with other things. The paired samples t-test you've been introduced to, and the one-way ANOVA comes at the end of the term. So this whole menu is kind of where we're living in this semester. And the first thing to compare the age of the average age of the teacher candidates who were surveyed on this instrument to the target age of 25, which is what we expect for a graduating teacher candidate, is the one sample t-test. So we look at the one sample t-test and it says, well, what do you want to test? That's your test variable. And what we want to test is age. And then it asks the test value, which is what age do you want to compare your sample age to it? Now we're going to say we want to compare it to 25. It's always useful to look at the options. The options here are not the missing value. We have no missing value, so we don't have to worry about that. We note you can change the confidence interval. So it will provide a confidence interval. The default is that it will provide a 95% confidence interval, but you can change that. And by the way, I should have stated this is a hypothesis of no difference. We're going to test it at alpha of 0.05, and it's non-directional. So we're now going to just say, okay, we're ready to perform this test in SPSS. And the first thing it will tell you is your descriptive statistics, and it will say that the mean age for these 74 people is 25.8 with a standard deviation of 7.447. And then it will perform the test of significance, comparing this test value to the sample mean. It will, for one thing, report what is the difference. That's the numerator of your one sample test statistic. And you'll see, oh, 25.8108 minus my target test value of 25 is 0.8108. So you see the results that would be replicated in these values. You see the standard error of the mean. If you want to, you can go back. You can, for instance, take this standard deviation, plug it into your formula for calculating the one sample t-test, for which you need the standard deviation or the standard or the variance for the sample, and divide that by the square root of n, and it should give you your standard error of the mean. So you have this box gives you all the data you need to calculate the t yourself. It's, well, actually, in addition to this. So the numerator of the t is this, the denominator is this, 0.86580 divided by, or I'm sorry, 0.81081 divided by 0.86580 is a little bit less than 1, is 0.936. 0.81 divided by 0.86, it's a little bit less than 1, gives you a t of 0.936. Your degrees of freedom for the test are n minus 1, 73. So these exactly match what you would get in a hand calculation of these data. It's just you got 74 people, so you don't want to do the hand calculation. So your decision, oh, and this, but the one thing is that this gives you the probability rather than the critical value. So what you do is you compare that probability to your alpha level. If it is equal to, which you'll probably never see, if it's, you can actually extend this to, by double clicking, to a whole lot of decimal places. So you can find, if it says 0.50, you can 0.05, you can extend it and see whether it's greater than or exactly, which it will never be. But if it's equal to or less than 0.05 and you have a two-tailed test, then you will reject the null hypothesis. If it's greater than 0.05 with an alpha of 0.05 and a two-tailed test, you will retain the null hypothesis. So the statistical decision in this case is to retain the null hypothesis. The confidence interval is provided. As I said, you have a choice of whether to do 95 or whether to provide your own breadth for the confidence interval. That is based on taking this mean value plus or minus the standard error times the critical test statistic. And SPSS doesn't give you the critical test statistic. It's buried in here somewhere. I mean, it has, SPSS has, you know, back rooms of binary tables, and it knows the critical value, but you would have to get your own critical value at degrees of freedom of 73 and alpha, 1 minus alpha of 0.95 to reconstruct this confidence interval yourself. However, you could. So I'm going to pause for a minute to catch my breath. Okay, so that is the one sample t-test. I would recommend that at any opportunity, you make up your own data. You try to do the hand calculations yourself. You load them into SPSS, or some of this stuff can be done in Excel, and you test your own results. It's something I do all the time. And also looking at the relationships between the input, something like the n, the mean, the standard deviation, all of which is enough to get you the standard error and the t statistic. Trying to recreate the t statistic from this information is very useful. So now I'm going to go on and test my hypothesis about the the Form A versus Form B. And I'm going to test this at alpha of 0.05, non-directional. I will maybe post some more, I'm going to right along be posting more SPSS videos from now on. So we'll get to interpreting one-tail tests in SPSS and other things. But now what we're going to do is we're going to look at the two sample test of the difference between two groups, two independent samples. And again, I'm going to find that under compare means. Here's the independent samples t-test. This is under analyze, compare means, independent samples t-test. And my test variable, the first thing I want to look at is whether this motivational form of the test affects reasoning. And that's my syllogism scale. Each of the items further up on the list are individual items using syllogisms, but I have a scale composed of those items, the average across items. So that's what I want to test is overall, is there a difference between the two groups on syllogisms as measured by this scale, which is the collection of items. So that's my test variable. Now, it wants to know what the groups are that I want to combine. And the groups are Form A and Form B. Now here it asks you this question mark. It says, how are the groups defined? And at this point, Bonner has to remember, what are the values given to these groups? I can't remember. So I'm going to have to cancel this out and go back to the original data and look and see how are these things coded, because for the group values, I need to know what numbers are in the data set. And the values are 1 and 2. So now I know, okay, there's a group with a value 1 and a group with a value 2. And that's what I want to compare. So I'm going back in to comparing means, independent samples t-test. I want to test syllogisms. And I'm going to group people according to the form. And I'm going to define the groups. One of them is group 1 and one of them is group 2. And I suggest that you always use specified values based on actual existing groups. The second choice is to artificially cut up your sample into groups, which I don't particularly approve of. So, and I covered that in other classes. So, but I know that for form, I have two groups. I have some people who were assigned to Form A, and that is numbered in the data set 1, and some people who were assigned to Form B, which is numbered in the data set 2. By the way, those have to be numbers. They cannot be letters. So that's important when you enter your data into the spreadsheet or statistical package. I'm going to check my options. It's always a good idea to check your options. Again, I have the confidence interval that I can manipulate, and I'm only doing one analysis where in a case where there's no missing data. So I can just continue from there. And now I can just say, okay, and my output comes up. The independent samples t-test is nice because just by default, without having to choose any special options, it gives you pretty much everything you might want. It tells you how many people responded to Form A versus Form B on the syllogism scale. For some reason that looks a little bit different from that's odd. Is that odd that this says that Form A occurs 38 times and Form B occurs 36 times? Oh, we lost a person. One person in Form A, see, something you should know. One person in Form A did not answer the syllogism questions. So our N for this test is 73. And you would want to say that. If you were doing all of these tests and you said, oh, I'm going to test against the target value for age of 25, N equals 74. For my independent samples test of means, I was testing the motivational form versus the non-motivational form on reasoning. And there was one person in the sample who didn't respond to the syllogism scale on reasoning as measured by the syllogism scale. There was one person who didn't respond. So my N was, and then really what you would do, you would report at that point your mean and standard deviation for each group. So you would say the 37 people responded to the motivational form of the syllogism questions, parentheses, M equals 2.4, comma, SD equals 0.83, close parentheses, and comma, and 36 people responded to the syllogism scale in form B, the non-motivational one, parentheses, M equals 3.25, comma, SD equals 0.31, close parentheses, comma, with one value missing from form A. That would be a very complete description. So let's go down. Oh, you also note that each of those has a mean, a standard deviation, and a standard error reported here to calculate the what do you call it? The standard error of the difference, which is provided right here. You need the standard deviation per group and the N per group. These are different N's, so I wouldn't recommend trying to calculate it yourself. But when we go down to the results of the test, the first thing you'll see that you have never seen before is Levine's test for equality of variances. That is not a t-test, not a z-test, it's an f-test. We're going to do f-tests later in the semester. You don't need to know anything about f-tests at this point, except this is tested with an f statistic. This is an assumption. Okay, so was one of the assumptions of the test of independent samples is that the two samples are independent. And another assumption is that the two samples have homogeneous variances. Their variances are the same within the bounds of chance. And the bounds of chance are just like with another test, they're usually assumed to be alpha of 0.05. So this, because this is an assumption, this is a case where you want to retain the null hypothesis. You want to be able to say, yeah, the difference between variance 1 and variance 2 is essentially 0. That's the null hypothesis with pretty much all the tests that you run. And that is what you hope as an assumption of this test, because otherwise you're violating something, you shouldn't run the test at all. So that's your Levine statistic is 0.553. And the significance level of it is 0.459. Now, just like any other test as reported on SPSS under this SIG column, if the SIG value is at or below 0.05, then you reject the null hypothesis. This value is above 0.04 or 0.05, so you retain the null hypothesis. This is a good thing for this particular test, for the test of equality of variances. You want to retain this test. You do not want this value to be below 0.05. So we're happy now. We can proceed to read the rest of the variables. And the t-statistic is minute. It's negative 0.04 approximately. Degrees of freedom, remember we had 73 cases because of the one missing. 73 minus 2 is 71. That's why the degrees of freedom are 71. The significance, so what you compare your alpha is 0.971, which is well within the boundaries due to chance. The mean difference is very small. The confidence level clearly goes across the value of 0, indicating that within a 95% confidence level, confidence interval, 0 is a likely value to occur, while 0 is what's under the null hypothesis. And even probable differences like negative 0.37 and 0.35 are not great. And so you retain the null hypothesis in this case, and you fail to achieve statistical significance. I want to just point out one more thing in here, which is that you have a row for equal variances not assumed, which is known as the Welch's test. And the Welch's test is used if you fail to meet Levine's assumption, or you fail to meet the assumption of equality of variances under the Levine's test. There are other tests of this. And so this value under SIG is less than 0.05. So then you haven't met this assumption. However, very nicely, by default, SPSS gives you an alternative test called the Welch's test. This is the second row under the results for the independent samples t-test, which basically what it has is it has results adjusted for the inequality of variances, and where that adjustment actually occurs is in these degrees of freedom. You don't need to worry about the technicalities of this, but if you fail to meet the assumption according to Levine's test on an independent samples t-test, then it is okay unless your unless you have a really egregious example, which is kind of a judgment call of a lack of homogeneity of variances. But it is appropriate to look at the Welch's test, which, like in this case, because in fact the variances were more or less equal, the results of the Welch's test are essentially no different than the results of the regular t-test. One thing is, you're not going to calculate Levine's test by hand, and you're not going to calculate the Welch's test by hand. But the Welch's test is used when Levine's test does not support the assumption of equality of variances. And I think that's all for this particular presentation. And I hope that it's helpful, and I will make another one as soon as possible.